Welcome to our deep dive into the science behind hurricanes. In this video, we will explore the fascinating processes that lead to hurricane formation, from the crucial role of warm water to the influence of low-pressure systems and the Coriolis effect. We'll also examine the structure of a hurricane, including the eye and eye wall, and discuss wind speeds and the different categories of these powerful storms. Additionally, we'll touch on storm surges, hurricane dissipation, and the seasonal frequencies that shape their occurrence. Join us as we uncover the science that drives one of nature's most dramatic phenomena. 1. Hurricane formation. Hurricanes begin their life over warm ocean waters, generally requiring temperatures of at least 26.5 degrees Celsius, 80 degrees Fahrenheit, to form. These storms thrive on a unique combination of environmental factors, including warm water, moist air, and low wind shear. When these conditions align, they create the perfect environment for a hurricane to develop and intensify. The warm ocean water evaporates, and as the moist air rises, it cools and condenses, releasing heat. This heat warms the surrounding air, causing it to rise and draw in more moist air from the ocean's surface, perpetuating the cycle. 2. The role of warm water. Warm ocean water serves as the primary fuel for hurricanes. As the surface water evaporates, it absorbs energy from the ocean and transfers it into the atmosphere. This process is akin to fueling a car. Without gasoline, the engine cannot run. Similarly, without warm water, a hurricane cannot sustain itself. The evaporated moisture condenses into clouds and storms, releasing latent heat, which intensifies the storm. The more warm water available, the more energy the storm can harness, leading to stronger winds and more intense rainfall. 3. Low-pressure systems. Hurricanes are low-pressure systems that form in tropical or subtropical regions. The process begins when warm, moist air rises from the ocean's surface, creating a vacuum that draws in more air. This continuous inflow of air contributes to the storm's rotation, influenced by Earth's rotation, which gives hurricanes their characteristic spiral structure. The warm air at the center rises rapidly, while cooler air rushes in to replace it, maintaining the low-pressure core. This dynamic of rising and sinking air is a hallmark of hurricane formation and strength. 4. The Coriolis effect. The Coriolis effect, a result of Earth's rotation, is crucial in the development of hurricanes. It causes these storms to rotate counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. This effect is like a spinning top. As the Earth spins, so does the atmospheric system, influencing the direction and spin of the storm. Without the Coriolis effect, hurricanes would not develop their distinctive spiral shape, nor would they achieve the organized rotation necessary for their development. 5. Eye of the hurricane. At the heart of every hurricane lies the eye, a calm, clear area at the center of the storm. This region is characterized by light winds and relatively calm weather. The eye forms due to the sinking air in the storm's center, where the air pressure is the lowest. It's an eerie calm amidst the surrounding chaos, often providing a brief respite during the storm. The eye's size can vary, but its presence is a defining feature of a mature hurricane, symbolizing the storm's intense power and organization. 6. Eye wall and wind speed. Encircling the eye is the eye wall, where the hurricane's fiercest winds and heaviest rainfall are found. The eye wall is like the fortress of the storm, housing the most intense weather conditions. Wind speeds in this area can exceed 150 miles per hour, 240 km per hour, in the most severe hurricanes. The eye wall's strength is a critical indicator of the hurricane's overall power and potential for destruction. The intense winds and rain here are responsible for much of the damage associated with hurricanes, emphasizing the storm's formidable nature. 7. Categories of hurricanes. Hurricanes are classified using the Saffir-Simpson scale, which ranks them from Category 1 to Category 5 based on wind speed. Category 1 hurricanes are the weakest, while Category 5 storms have sustained winds of 157 miles per hour, 252 kilometers per hour, or higher. This scale helps convey the potential severity of a storm to the public and emergency responders. Understanding these categories is vital for preparation and response efforts, as each level brings different threats and challenges to affected areas. 8. Storm surges. One of the most dangerous aspects of a hurricane is the storm surge, a rise in sea level caused by the storm's strong winds. As the hurricane pushes water toward the shore, it can lead to significant flooding, particularly along coastlines. Storm surges are often the deadliest part of a hurricane, causing extensive damage and loss of life. They highlight the importance of evacuation and preparedness efforts in coastal areas, as even a slight rise in water level can have catastrophic consequences. 9. Hurricane dissipation. Hurricanes gradually lose strength when they move over cooler waters, land, or areas with high wind shear. Without the warm water and moist air that fuel them, they weaken and eventually dissipate. This process is akin to a fire running out of wood to burn. Without fuel, the fire fades away. Understanding the factors that lead to hurricane dissipation is essential for predicting the storm's lifespan and potential impact on land. 10. Hurricane seasons and frequency. Hurricane seasons vary by region, with the Atlantic Ocean season running from June to November. The peak occurs between August and October when warm ocean waters are most abundant. While hurricanes can form at any time, their frequency and intensity increase during these months. This seasonal pattern underscores the importance of monitoring ocean temperatures and atmospheric conditions to anticipate potential storms and prepare accordingly. Understanding the science behind hurricanes is vital for improving forecasting and minimizing their impact. These powerful storms are products of complex natural processes, and knowledge of these processes enhances our ability to respond effectively.